Something is out there, past Neptune, past every planet we have ever named, a world 10 times heavier than Earth, so far away that 1 year on its surface lasts longer than all of human civilization. We have never seen it, but its fingerprints are everywhere. 6 distant, frozen worlds all point toward the same invisible force. Our entire solar system is tilted by 6 degrees, and nobody could explain why. Until now, we are going to follow the signals, meet the scientists chasing them, and ask the question that keeps astronomers awake at night. If you enjoy the ride, like and subscribe. Planet 9, let's go. You already know the 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. That is the solar system, right? 8 planets, 1 sun, done. That is what most people think. And for most of human history, that is exactly what we thought too. But the solar system does not end at Neptune. It keeps going. Way, way farther than most people ever imagine. Past Neptune, there is a massive ring of frozen objects called the Kuiper Belt. Past that, there is an even larger shell of icy debris surrounding the entire solar system called the Oort cloud. These regions stretch so far from the sun that light from our star barely reaches them, and somewhere out there, hiding in that darkness, something enormous might be waiting. This is the story of Planet 9, a world that has never been directly seen, photographed, or confirmed, a planet predicted entirely from math. A ghost planet whose gravity is bending the paths of distant frozen worlds from billions of miles away. Think about that for a second. We are not just talking about a small rock floating somewhere in the dark. Scientists believe this object is roughly 10 times heavier than Earth. That puts it in the category of what astronomers call an ice giant, similar in size and mass to Uranus and Neptune. A full, proper planet, hiding right inside our own solar system. And the craziest part? The evidence has been building for over a decade. The search for Planet 9 starts at the edge of the Kuiper Belt, in a zone called the extreme outer solar system. This region sits so far from the sun that it would take a commercial airplane roughly 5 million years to get there. The sun, from that distance, would look like a bright dot in the sky, roughly the same size as a star you might see on a clear night. There would be almost no warmth, no light to speak of, just cold, dark, and silence. Objects that live in this zone move extraordinarily slowly. Not slow the way a car moves through a school zone. Slow the way a glacier moves, where you have to watch for years just to notice a change. These objects take thousands of years just to complete a single loop around the sunday. Now, here is where things get strange. When astronomers mapped out these distant frozen objects, they expected to see something random, objects scattered in every direction, orbits pointing all over the place, nothing in particular connecting them. That is what you would get if nothing were out there influencing them. Pure chaos. That is not what they found. Instead, the orbits of the most distant objects were grouped together, all pointing in the same direction, all tilted at nearly the same angle, moving in a pattern so precise that the odds of it happening by chance are astronomically small. Something was organizing them, something massive, with enough gravitational muscle to reach across billions of miles and line these frozen worlds up like magnets pointing north. Scientists had 2 choices. Either the laws of physics were wrong, or there was something out there. Most researchers chose the second option. They ran the numbers, they built models, they predicted a planet roughly 46.5 billion miles from the sun, sitting in a stretched, oval orbit so enormous it takes between 10,000 and 20,000 years to complete 1 lap, a planet that nobody had ever seen, a planet that math alone suggested had to exist. The edge of our solar system was hiding something, and astronomers were only beginning to understand how deep the mystery went, because the more they looked, the weirder it got. Picture 6 compass needles. You scatter them randomly on a table. You would expect them to point in 6 different directions, because nothing is pulling them. But when you come back and every single needle points north, you know something magnetic is nearby. That is exactly what astronomers found at the edge of our solar system. In the region beyond Neptune, researchers identified 6 extreme distant objects. These are not ordinary asteroids or simple Kuiper belt rocks. These are massive frozen bodies traveling in long, stretched orbits that take them far beyond the reach of Neptune's gravity. Scientists call them extreme trans-Neptunian objects. But the name matters less than what they are doing. What they are doing is shocking. All 6 of these distant bodies travel in elliptical orbits that point in the same direction in space. On top of that, their orbits are all tilted in the same way, roughly 30 degrees downward compared to the flat plane where the main planets orbit the Sunday. 6 separate objects, formed in different places, moving at different speeds, and yet somehow all aligned like they are following instructions from a source nobody can see. Astronomers calculated the odds. The probability of 6 objects randomly ending up in this precise configuration is less than 1 in 14,000. That is roughly the same odds as flipping a coin 13 times and getting heads every single time. Something is pulling them into formation. Think of it like this. You are watching 6 boats drifting in the ocean. They all drift from different corners of the sea, but somehow every single boat ends up pointing bow first toward the same empty patch of water. You cannot see anything there. The water looks calm, but clearly, something below the surface is generating a current strong enough to redirect all 6. That something, in the case of our solar system, would need to be massive. Astronomers ran gravitational models and calculated that whatever is organizing these orbits would need to have roughly 10 times the mass of Earth. A small rocky asteroid could not do this. A cloud of space dust could not do this. The math kept pointing to one answer: a large, hidden planet. This was the first major piece of evidence, and by itself, it was already hard to ignore. But here is what made astronomers sit up straighter. When they looked at where this invisible object would need to be positioned to create this pattern, the math gave them a location. A general region of space, vast but defined, somewhere in the outer darkness of the solar system on the opposite side of the sun from the clustered objects. They had a direction to look. The problem was looking. The region of space they were targeting sits so far from Earth that even our most powerful telescopes struggle to see anything there. The distances involved are almost impossible to feel. Neptune, the farthest confirmed planet, is about 2.8 billion miles from the Sunday planet 9, if it exists, would be roughly 46.5 billion miles away. That is more than 16 times farther than Neptune. At those distances, a planet the size of Neptune would appear almost completely dark. No reflected sunlight bright enough to catch, no clear signal, just an incredibly faint smudge, if anything, buried in a sky full of background stars. The search was on, and it was going to be harder than anyone expected, because, as astronomers would soon discover, 6 aligned objects were only the first clue. The solar system itself was hiding something even stranger. In January of 2016, 2 astronomers at the California Institute of Technology sat down and published a paper that changed the conversation about our solar system forever. Their names were Konstantin Batygin and Mike Brown, and their paper made a bold claim: a 9th planet existed, and they had never seen it. This might sound impossible. How do you discover a planet you cannot see? The answer is the same method that found Neptune 170 years earlier: pure mathematics. Here is how it worked for Neptune. In the 1800s, astronomers noticed that Uranus was wobbling. Its orbit was off. It was not traveling the path it should travel given the gravity of every known planet. Something was tugging on it from farther out. Astronomers did the math and calculated exactly where a hidden planet would need to be to cause that wobble. They pointed a telescope at that exact location, and there was Neptune, right where the math said it would be. Batygin and Brown did something similar, but on a scale that dwarfs the Neptune discovery. Instead of one wobbling planet, They had 6 distant frozen objects behaving strangely. They fed the orbital data from all 6 into their models. They calculated what kind of gravitational source could organize those 6 objects into their precise, aligned configuration. The math kept returning the same answer: a massive planet on an extreme elongated orbit, sitting far beyond the Kuiper belt. The calculations gave them a rough mass, roughly 10 times that of Earth. They got a rough orbital size, taking somewhere between 10,000 and 20,000 years to complete one loop around the Sunday. And they got a rough location in the sky where this planet should be hiding. Batygin described the moment they ran the simulation and watched the pattern emerge. The orbits of the 6 distant objects, which should have scattered apart over billions of years, stayed stable. Something was holding them. The model worked. The planet was real, at least on paper. Mike Brown, for his part, had a personal reason to care about this discovery. He was the same astronomer who had led the team that discovered Eris in 2005, the dwarf planet whose existence helped trigger the reclassification of Pluto. Brown had technically been responsible for our solar system going from 9 planets to 8. The idea that his own research might now restore a 9th planet was not lost on him. The 2016 paper spread fast. News outlets picked it up. Scientists around the world began reviewing the math. Most of them agreed it was sound. The logic was tight. The model was elegant. But here is the thing about predicting a planet with math. The prediction is only the beginning. Neptune was confirmed within months of the prediction because it was close enough and bright enough to spot quickly. Planet 9 sits vastly farther away. It took humanity over 170 years after the discovery of Neptune to find objects distant enough to even hint at this new planet. Finding the planet itself could take years or decades. The math said it was there. The telescopes just needed to catch up. And while the world waited, a quieter question was growing louder. Because even if the planet was real, there was a deeper mystery buried inside the data. Something that went beyond a hidden planet. Something wrong with the solar system itself. Distance in space is hard to feel. When someone says Planet 9 is 46.5 billion miles from the Sun, that number means almost nothing to most people. It is too big, too abstract, so let us try to make it real. The Sun sends light in every direction at the same time. That light travels at about 186,000 miles per second. It takes 8 minutes for that light to cross from the Sun to Earth. 8 minutes. At the fastest speed anything in the universe can travel. It takes that same light over 4 hours to reach Neptune. That is how far Neptune is. You could watch a full movie and then another full movie, and the light leaving the Sun right now still would not have reached Neptune. For Planet 9, the journey would take over 6.5 hours, one way, and that is if it is at the near end of its enormous oval orbit. At its farthest point from the Sun, the light travel time stretches toward a full day. Now think about what that means for the planet itself. The sunlight reaching Planet 9 would be so weak that the planet sits in near total darkness. The Sun, viewed from the surface of Planet 9, would appear as nothing more than a very bright star, slightly brighter than the other stars in the sky, but nowhere near the blazing disk we see on Earth. There would be no warmth from it, no glow, just a cold, distant pinpoint of light in an otherwise black sky. Temperatures in that region of space drop to near absolute zero. That is roughly negative 455 degrees Fahrenheit. At that temperature, gases like methane and nitrogen freeze solid. They do not drift as gas or pool as liquid. They crystallize into ice, coating whatever surface is out there. If Planet 9 is an ice giant, its outer layers would be thick blankets of hydrogen and helium gas, wrapping around a deep core of frozen rock and ice. Storms would rage on its surface, but they would be dark, cold, and invisible to us. No warm sunlight to drive the kind of colorful weather bands we see on Jupiter or Saturn. The planet would also be essentially invisible to traditional telescopes. Telescopes searching for planets usually look for reflected light. A planet shines because sunlight bounces off it. But at the distances involved with Planet 9, sunlight arrives so weakly that the reflected signal would be almost impossible to distinguish from background noise. Put it this way, if you stood a mile away in total darkness and tried to see a black basketball painted to absorb light, you would have a better chance of finding it by feel than by sight. That is roughly the challenge astronomers face. And yet, the planet, if real, would still exist, still be out there, slowly crawling along its enormous orbit, taking tens of thousands of years to complete one lap. At its current estimated distance from the Sun, Planet 9 has probably completed only a handful of full orbits since the solar system formed. While Earth has gone around the Sun 4.5 billion times, Planet 9 may have only completed a few 100,000 laps. On the scale of the universe, it barely moves. That stillness is part of what makes it so hard to find. But there was one way to look that did not depend on reflected light at all, and that idea was about to change the search completely. Here is something most people never learn in school. The 8 planets of our solar system are not perfectly lined up with the Sunday. You would expect them to be. The Sun sits at the center, and the planets formed from a spinning disk of gas and dust around it billions of years ago. Everything in that disk should have settled into the same flat plane, aligned with the Sun's own equator. That is how physics works. Spinning systems flatten out, disks align, except ours did not. The entire orbital plane of the planets is tilted 6 degrees relative to the Sun's equator. 6 degrees does not sound like much, but remember, we are talking about the combined orbit of 8 planets, each one a world in its own right. For all of them to be collectively tilted means something pushed the whole system sideways at some point in history. Astronomers noticed this tilt decades ago. For a long time, nobody had a good explanation. Then came the Planet 9 models. When researchers ran simulations of a massive planet sitting on a far outer orbit, tilted and stretched, something fascinating happened. Over billions of years, the gravitational influence of that distant planet slowly dragged the inner solar system, like a hand pressed against a spinning top, nudging it degree by degree over an enormous stretch of time. The simulation showed the planets gradually shifting away from the Sun's equatorial plane. After billions of years of that gentle, constant pull, the inner solar system ended up tilted by roughly 6 degrees, exactly the tilt we actually observe. This was a second piece of evidence, completely independent from the clustered orbits of the distant icy objects. 2 completely separate observations, 2 unexplained mysteries, and 1 proposed planet that solved both of them at the same time. That is when serious astronomers started paying close attention. Think of it like solving a mystery, where 2 unrelated witnesses describe the same suspect without ever talking to each other. One witness says the suspect had a red jacket. The other describes a red jacket from a different angle, without knowing what the first one said. Suddenly, the story gets a lot more believable. Planet 9 was wearing a red jacket. The solar tilt discovery gave researchers something important: mathematical confirmation that whatever was causing the distant orbit clustering was also powerful enough and old enough to have shaped the entire planetary system, something that has been sitting out there, pulling on everything for billions of years. But that raised an uncomfortable question. If something that massive has been in our solar system for billions of years, how did it end up so far out? Where did it come from? Most planetary formation models suggest planets form close to the Sun, where the raw material is densest. A planet 10 times heavier than Earth, forming at the distance of Planet 9, seems extremely unlikely. Something must have happened to push it outward. The leading idea is that early in the solar system's history, Planet 9 formed closer in, near the other gas giants. A gravitational interaction, possibly with Jupiter or the young Sun itself, flung it outward. A cosmic billiard ball, knocked into the dark, and then it stayed there, slowly orbiting in the cold, leaving only mathematical fingerprints on everything it passed. The deeper astronomers dug, the more fingerprints they found. In the year 2003, a team of astronomers discovered something strange. They found an object in the outer solar system that defied easy explanation. It was a large, reddish body following an orbit so stretched and distant that it spent its entire existence far beyond Neptune's reach. They named it Sedna, after the Inuit goddess of the sea. Sedna was puzzling because, according to the standard model of our solar system, objects that far out should have been scattered there by Neptune's gravity long ago. But Sedna never gets close enough to Neptune for that to have happened. Its orbit sits well beyond Neptune's gravitational reach, implying it was nudged into that position by something else entirely. Objects that behave like Sedna are called sednoids. They live in a zone so remote that almost nothing we know about can push or pull them. They are essentially isolated from the rest of the solar system, untouched. And recently, astronomers found another one. Using the Subaru telescope in Hawaii, a team identified a new sednoid designated 2023 KQ-14. This object never gets closer than 6.6 billion miles to the Sunday. For reference, Neptune orbits at roughly 2.8 billion miles. This object's closest approach is more than twice that distant. Its entire orbit takes place in a zone of isolation that should be gravitationally quiet. Here is the twist. 2023 KQ-14 has a highly stable orbit. It is moving in a smooth, predictable path that has likely remained unchanged for an enormous stretch of time. That stability is a problem for Planet 9. If a massive planet were sitting close to this sednoid's orbital path, its gravity would be tugging on that path constantly. Over millions of years, those repeated tugs would distort the orbit, making it wobbly, unpredictable, messy. The fact that this sednoid's orbit is so clean and stable suggests there is no large disturbing planet nearby. That sounds like bad news for the Planet 9 theory, but it is actually more complicated than that. If Planet 9 exists, and its orbit is stable too, it might be sitting in a position that passes nowhere near 2023 KQ-14. A planet on an enormous, elongated orbit spends most of its time at the far end of that orbit, far from the objects it influences. So the sednoid's calm path might simply mean that Planet 9's orbit does not overlap with this particular region of space. What 2023 KQ-14 actually forces scientists to do is recalculate. If this sednoid is undisturbed, Planet 9 must be either farther away than initial models suggested, or on a different orbital path than previously mapped. The discovery shrank the list of possible locations. It also pushed the predicted location of Planet 9 even deeper into the dark, which made the search harder. But it also added a new piece to the puzzle. Because multiple stable sednoids existing out there, all undisturbed and quietly orbiting, tells us something important. The extreme outer solar system is not as chaotic as it should be. Something organized it long ago, something that swept through once and left these objects in stable paths, before retreating to a distance where its influence faded. That is the fingerprint of a planet on a very long, very slow orbit. The ghost was still there, just harder to pin down. Finding a planet sounds simple enough. Point a powerful telescope at the sky. Look for something large and round. Done. But finding Planet 9 is nothing like that. Every planet we have ever discovered in our solar system was found because of light. Either light the planet reflected from the sun, or in the case of some exoplanet searches, light the planet blocked as it passed in front of its star. Vision at every step. Even Neptune, which sits roughly 2.8 billion miles away, was bright enough for telescopes of the 1800s to spot once astronomers knew roughly where to look. Planet 9 is a completely different problem. The amount of light a planet reflects depends on two things: how bright the light source is, and how far away the planet sits from that source. Move a planet twice as far from the sun, and it reflects 4 times less light. Move it 10 times farther, and it reflects 100 times less light. Planet 9 sits over 16 times farther from the sun than Neptune. That means it reflects hundreds of times less light than Neptune does. Neptune itself is already faint in our sky. You need binoculars just to make it out as a tiny blue dot. Now imagine something reflecting hundreds of times less light than that faint dot. You are now hunting for something essentially invisible, against a background sky full of billions of stars and galaxies. Every time a telescope scans that part of the sky, it picks up thousands of background objects, stars, distant galaxies, nebulas. Any one of them could be mistaken for a slow-moving planet, and a slow-moving planet could easily be dismissed as another background object. Separating the signal from the noise requires multiple observations over months or years, watching to see if any faint smudge moves against the background stars in the slow, gradual arc of a solar system body. It is like trying to find a dark grey piece of felt on a dark grey carpet in a dark room, using a flashlight whose batteries are almost dead. And it gets worse. The region of sky, where Planet 9 is predicted to hide, sits close to the bright band of the Milky Way in certain sky positions, which floods that zone with extra background stars. Trying to spot a faint moving object in front of the densest part of the galaxy is like trying to find one specific firefly in a stadium with the lights on. Astronomers have tried. Multiple survey teams have scanned the predicted zone. The Dark Energy Survey, the Pan-STARRS telescope in Hawaii, and several other projects have covered significant portions of the predicted search area. Every scan so far has come up empty. That does not mean the planet is not there. The search area is enormous. Even the most thorough surveys have covered only a fraction of where Planet 9 might be hiding on its long orbit. The planet could be sitting in an area not yet scanned, or it could be near the farthest point of its orbit right now, making it even dimmer and slower moving than usual. What was becoming clear was that finding Planet 9 with reflected light alone was going to be nearly impossible with existing technology. Scientists needed a new strategy, one that did not rely on the planet bouncing sunlight back at us. They needed to listen for its heat. When something is warm, it glows. You cannot always see that glow with your eyes, but it is there. A campfire glows orange and red. A living human body glows in infrared, which is why night vision cameras can see people in the dark. Even a brick wall, sitting in sunlight during the day, radiates heat you cannot see, but an infrared sensor can detect clearly. Planets work the same way. Every planet in the solar system generates some level of internal heat. This heat comes from the original energy of formation, the slow settling of the planet's own mass, and in some cases, from radioactive decay deep inside the core. Jupiter radiates almost twice as much heat as it receives from the Sunday Neptune, also pushes out more heat than it absorbs. These giant worlds are warm engines, quietly glowing in infrared even when sunlight barely touches them. If Planet 9 is an ice giant, similar to Uranus or Neptune, it should be doing the same thing. Even sitting at 46.5 billion miles from the Sun, in darkness that makes our coldest winters feel tropical, the planet would still radiate a faint glow of thermal energy, a gentle warmth leaking outward into space. That warmth can be detected, not with ordinary visible light telescopes, but with instruments tuned to far infrared wavelengths. Think of it as astronomical heat sensing. Instead of looking for the planet by the light it reflects, this method looks for the heat it produces. The challenge is that this thermal signal would be extremely faint. The planet sits in a region of space that is already near absolute zero, meaning the background temperature is as cold as the universe gets. The planet's own warmth would be only slightly above that background, like trying to detect the heat of a single birthday candle inside a freezer the size of a football stadium. To even attempt this, astronomers needed a telescope specifically designed to detect far infrared light, cooled to near absolute zero itself, so that the telescope's own warmth would not drown out the signal it was trying to measure. And they had one. The Japanese space telescope Akurai was launched in 2006 and spent years mapping the entire sky in infrared. The instrument was cooled using liquid helium, dropping its sensors to just a few degrees above absolute zero. At those temperatures, it could pick up thermal signals too faint for any ground-based telescope to measure. Researchers went back through the Akeri data, along with archival data from an older infrared satellite launched decades earlier, and began cross-referencing points in the sky where Planet 9's models predicted it should be. The search was painstaking. Every point of infrared light in the predicted zone had to be examined. Every candidate had to be checked against known objects, stars, galaxies, known asteroids. One by one, the list of unexplained signals shrank, until 2 candidates were left, 2 points of infrared light, no visible counterpart, no known object at those positions in any catalogue, located in the general region of space, where Planet 9's orbit was predicted to pass. The thermal hunt had found something, but 2 candidates is very different from 1 confirmed planet, and what came next was going to test everyone's patience. In early 2025, a team of researchers published results that sent a jolt through the planetary science community. After analyzing decades of far-infrared sky survey data, they had narrowed the search for Planet 9 to 2 specific candidates. Both were detected in data from the Akari Space Telescope, cross-referenced against older infrared observations from the 1980s. Here is why this matters. A moving object in the solar system, when photographed at 2 different times separated by years, appears to have shifted position against the background stars. This is called proper motion. The Akari team found 2 infrared signals that appeared in one dataset but not in the other, or appeared in slightly different positions between the 2 surveys. That kind of positional shift is exactly what you would expect from a slow-moving body inside our own solar system rather than a distant, stationary background source like a galaxy. Both candidates showed the kind of faint, cold thermal glow consistent with a large icy planet sitting at an enormous distance from the Sunday. The temperature signature matched what Planet 9 models predicted. The positions fell within the general region of sky where the gravitational models said the planet should be. For a few weeks, the excitement was genuine, but astronomy demands confirmation, and confirmation requires multiple independent observations. When other teams turned their instruments toward the 2 candidate positions, the results were frustrating. Some follow-up observations could not clearly detect either candidate. Others found faint signals but could not confirm they were moving objects. The data was ambiguous. Part of the problem was the limitations of the original Akari telescope. It was a remarkable instrument for its time, but its resolution was limited. A faint infrared smudge in Akari data could be a distant planet, or it could be a faint galaxy, a known asteroid just outside the catalog boundaries, or even an instrumental artifact from the detector itself. Without sharper follow-up imaging, pinning down the exact nature of either candidate was extremely difficult. Both candidates remain unresolved. Neither has been ruled out. Neither has been confirmed. What the Akari search did accomplish was something important, even without a confirmed discovery. It demonstrated that the thermal search method was viable. It showed that far-infrared surveys could find candidates in the predicted zone. It gave the planetary science community a concrete reason to push for better infrared telescope time, and it sharpened the predicted location of Planet 9 based on where the candidates appeared. Every piece of data, even ambiguous data, narrows the search. Researchers are now advocating for follow-up observations using newer, more powerful infrared observatories. The James Webb Space Telescope, the most powerful space telescope humanity has ever launched, is theoretically capable of detecting the thermal signature of Planet 9 if pointed at the right location. The challenge is getting enough telescope time in the right direction, a difficult ask for an instrument with thousands of competing science programs from researchers around the world. But the Akari results showed something else too. They showed that the search was not hopeless. 2 candidates, both unexplained, both sitting in the predicted region, both still open questions. And open questions in science have a way of demanding answers. The race was not over, but it was about to get a reality check, because the sheer physical scale of this problem was something no telescope, however powerful, could simply fast-forward past. In January of 2006, NASA launched a spacecraft called New Horizons. Its mission was to fly past Pluto, which it did in July of 2015, sending back the first close-up images of that distant world. After Pluto, New Horizons kept going, flying deeper into the Kuiper Belt and making a close pass of a distant object nicknamed Arrokoth in January of 2019. New Horizons is fast, very fast. At its peak speed after launch, it was traveling at roughly 36,000 miles per hour. That is fast enough to cross the continental United States in about 4 minutes. It is the fastest spacecraft ever launched by humanity. It is still not fast enough. At that speed, New Horizons would need roughly 118 years just to travel the distance to where Planet 9 is estimated to be. 118 years. That is longer than most countries have had airplanes. It is longer than most modern nations have had functioning electricity grids. And that assumes Planet 9 is at the near end of its orbit right now. If the planet is near the far end of its enormously stretched path, the distance grows even larger and the travel time stretches past 200 years. This is one of the most humbling realities of the Planet 9 search. Even if we confirmed the planet's exact location tomorrow, even if we launched the most powerful rocket ever built the following day, a probe sent to visit it would not arrive until well into the next century. The scientists who designed that mission would likely never see the results. It would be a gift from one generation of astronomers to the next. The distance puts physical exploration completely out of reach for now. There is no shortcut, no faster option. Physics does not allow it at our current level of technology. The only way to learn about Planet 9, at least for the foreseeable future, is to observe it from Earth using telescopes. But even that is not straightforward. New Horizons itself gives us a sense of scale. After more than 19 years of travel, New Horizons has covered roughly 5 billion miles from Earth. That sounds enormous. And it is. By any human measure, Planet 9 is predicted to sit about 46.5 billion miles from the Sunday. New Horizons has traveled roughly 1/10 of that distance in 19 years. To put it bluntly, we have barely left the driveway. There is a reason astronomers have been focused almost entirely on remote detection methods: thermal imaging, gravitational modeling, infrared surveys. None of these require going anywhere. They are all ways of learning about an object so impossibly far away that the only tool humanity currently has is light, and even light takes over 6 hours to make the journey. What this distance really tells us is something deeper about the nature of the problem. Planet 9, if real, exists in a realm that is genuinely alien to human experience. A place so cold, so dark, and so far removed from the inner solar system that it might as well be in a different world entirely. And yet it is supposedly part of our solar system, part of the same cosmic family as Earth, right here in our own backyard, by the standards of the galaxy. That thought alone should be unsettling, and the next discovery made it even more so. Every planet in our solar system orbits the Sun in the same direction, counterclockwise. If you look down at the solar system from above the North Pole, this shared direction is not a coincidence. All those planets formed from the same spinning cloud of gas and dust, and they inherited that spin. Like water draining in a bathtub, the original rotation set the direction for everything. Most asteroids, comets, and Kuiper Belt objects follow the same rule, counterclockwise, aligned with the flat disk of the solar system. It is the default setting for objects formed in this solar system. Some objects do not follow that rule. Far out in the Kuiper Belt and beyond, astronomers have discovered bodies that orbit in the opposite direction, clockwise, moving against the general flow of the solar system. These are called retrograde objects. A few of these exist closer in, and astronomers can usually explain them as objects that got gravitationally flipped by close encounters with giant planets. Jupiter and Saturn have enough gravitational force to occasionally knock a small body into a backwards orbit. But the retrograde objects found in the extreme outer solar system are different. They are too far away from Jupiter or Saturn for those planets to have flipped them. No known gravitational source out there could have pushed an object into a backwards orbit and then left it undisturbed. Some of these distant retrograde objects are also tilted at extreme angles. Instead of orbiting in the flat plane of the solar system, they travel at angles of 60, 70, even close to 90 degrees compared to the main disk. These are objects that practically orbit vertically around the Sun, like a coin spinning sideways instead of lying flat. Achieving an orbit that tilted that far out requires an enormous gravitational kick, the kind of kick that only something very massive could deliver. Researchers built simulations to test whether a distant, massive planet could produce these retrograde and extreme tilt orbits naturally. They found that it could. The gravitational interactions between a Planet 9-like object and bodies scattered throughout the outer solar system, played out over billions of years, could occasionally flip objects into backwards and high-angle orbits, at roughly the rate actually observed. The match between the simulations and the real observations was uncomfortably close. Uncomfortable, because it meant the evidence was piling up from multiple directions. The clustered orbits, the solar system's 6-degree tilt, the stable sednoids, and now these twisted backwards orbiters, each one a small piece of a pattern that kept pointing toward the same invisible source. A planet that has been sitting out there for billions of years, silently reshaping everything near it. Think of it like coming home and finding furniture rearranged. Nothing dramatic, just small shifts. A chair 2 inches to the left, a lamp facing a different direction, a book on the wrong shelf. Individually, each change means little. Together, they tell you somebody was here. The solar system was rearranged. The question was not whether something had done it. The question was exactly what that something was. Because the more carefully researchers looked, the stranger that question became. Let us go back to that 6-degree tilt and really sit with it. The Sun rotates on its own axis. It spins roughly once every 25 days at its equator, a little slower near its poles. That spinning Sun has an equatorial plane, meaning an imaginary flat line running around its middle, the same way Earth's equator runs around ours. When the planets formed 4.5 billion years ago, they built themselves from a disk of gas and dust that was spinning in alignment with the young Sunday. The disk flattened out, the planets formed inside it. Everything should sit on the same level, perfectly aligned with the Sun's equatorial plane. Everything is off by 6 degrees. Imagine taking a dinner plate and tilting it slightly, then filling it with 8 peas arranged in a ring. All 8 peas are on the plate, all in a ring, but the whole plate is tilted away from you. That is roughly the situation of our solar system. The 8 planets orbit in a ring around the Sun, but the plane of that ring is tilted 6 degrees away from where physics says it should be. For decades, this was a known anomaly without a good explanation. No process in standard solar system formation theory naturally produces a misaligned planetary disk. Astronomers catalogued it, filed it away as a curiosity, and moved on. Then came the Planet 9 simulations. A massive planet on an extreme outer orbit does something counterintuitive. Its gravity does not just tug on nearby objects. Over billions of years, its slow, constant pull works like a hand pressing on the edge of a spinning gyroscope. A gyroscope does not fall over when you press on its edge. Instead, it slowly tilts and precesses, the whole axis drifting in a circle over time. The inner solar system behaves similarly under the long-term influence of a distant, massive planet. The gravitational torque from Planet 9, applied gently over 4 billion years, would slowly drag the entire orbital plane of the inner planets away from the Sun's equatorial alignment. The simulations predicted the magnitude of this tilt: 6 degrees. Real-world value, observed for decades: 6 degrees. 2 things pointing at each other from completely different directions. This is what physicists call a convergence. It is one of the strongest forms of indirect evidence in science. 2 separate, unexplained observations, predicted and explained by the same model. But there is a twist worth knowing. The 6-degree tilt does not prove Planet 9 exists. It proves that if Planet 9 is real and sits roughly where the models predict, then the tilt is naturally explained. The logic runs only one way. But it is a powerful constraint. Whatever caused the tilt, it has been doing so for billions of years. It has been massive enough and distant enough to influence the entire system without anyone noticing. Like a neighbor who has been quietly adjusting the fence line between your yards by 1 millimeter a year for 40 years. You would never notice in real time, but the cumulative result is unmistakable. 6 degrees, 46.5 billion miles away. Billions of years of invisible influence. And that was just what it did to the planets. What it may have done to the objects at the very edge of the solar system was far more dramatic. Most people picture a planet as a solid ball you could walk on, rocky ground, maybe a crater or two, mountains in the distance. Planet 9 would be nothing like that. If it is an ice giant, and that is what the mass estimates strongly suggest, it would look more like Uranus or Neptune than like Earth or Mars. Something between a gas ball and a frozen world, layered in ways that feel deeply alien. Start from the outside and work inward. The outermost layer would be a thick atmosphere of hydrogen and helium gas, the two most abundant elements in the universe. This atmosphere would be enormous, stretching thousands of miles deep before you hit anything denser. Winds in this layer could reach hundreds of miles per hour, even on a calm day by Earth standards, driven not by sunlight but by heat leaking out from the planet's interior. Deeper in, the pressure increases. The gases that were floating freely near the surface start to compress. Methane gas, which exists in this region of space, begins to freeze out of the atmosphere in crystals. These methane ice clouds would give the planet a bluish tint, similar to the blue of Uranus and Neptune, which get their color the same way. Go deeper still, and you reach what scientists call the water ammonia ocean. Despite the name, this is nothing like an ocean on Earth. The pressure and temperature at this depth turn water and ammonia into a hot, dense, electrically conducting fluid. This layer is thought to be responsible for generating the magnetic fields of ice giant planets, because the electrically charged fluid moves around in ways that act like a giant wire coil wrapped around the planet. At the very center sits the core, solid, dense, compressed rock and ice under pressures so extreme that normal chemistry no longer applies. The core of an ice giant is probably about the size of Earth, but it contains almost none of the open space or light rock that makes Earth habitable. It is a compressed ball of matter sitting under conditions that no laboratory on Earth has ever recreated. The whole structure, from outer atmosphere to core, would span a distance roughly 3 to 4 times the diameter of Earth. If you set Planet 9 next to Earth, Earth would look like a tennis ball next to a basketball. There would be no surface to stand on. You could fall through the outer atmosphere for thousands of miles, and the layers below would just get denser and hotter until you were crushed by the pressure long before you reached anything solid. And all of this would be happening in almost total darkness. No sunlight warming the cloud tops. No warmth reaching down from above. The planet's only significant heat source would be its own internal energy, slowly leaking outward from the core. From the outside, viewed through a telescope, it would look like a faint blue-grey sphere, slightly warmer than its surroundings, quietly drifting in one of the loneliest places in the solar system. That world is sitting out there right now, in the dark, waiting, and it has been waiting for a very, very long time. Humans have been recording history for roughly 5,000 years. Civilizations rose and fell. Languages were born and died. Empires covered the earth and then crumbled to dust. All of recorded history, every war, every invention, every empire, every moment written down or carved into stone, fits into about 5,000 years. 1 year on Planet 9 takes longer than that. A year on any planet is just the time it takes to complete one full orbit around the Sunday Earth. It takes 365 days. Mars takes about 2 Earth years. Jupiter takes 12. Saturn takes 29. Neptune, the farthest known planet, takes about 165 Earth years to complete one loop. Planet 9 is estimated to take between 10,000 and 20,000 Earth years to complete a single orbit. At the lower estimate, That is twice the entire span of recorded human history for every single year on Planet 9. At the upper estimate, it is 4 times as long. To feel this properly, think about where humanity was 10,000 years ago. Agriculture had barely started. Humans were transitioning from hunting and gathering to farming small settlements. The wheel had not been invented yet. Writing did not exist. The Great Pyramids of Egypt were still 5,000 years in the future. That is how long 1 year takes on Planet 9. Now, consider that since the solar system formed about 4.5 billion Earth years ago, Planet 9 has likely completed somewhere in the range of 200,000 to 450,000 orbits. That sounds like a lot until you realize Earth has completed 4.5 billion orbits in that same time. Planet 9 has gone around the Sun roughly 10,000 times fewer than Earth has. This extreme orbital period creates a serious problem for astronomers. To pin down exactly where a planet is in its orbit, you need to observe it over a significant portion of that orbit. For Earth, you can watch a discovered object complete a full orbit in 1 year. For Neptune, you need 165 years. And astronomers have managed that by combining old observations with new ones. For Planet 9, watching even a tiny fraction of its orbit would take thousands of years of continuous observation. Human civilization has only been doing organized astronomy for a few centuries. Even the most ancient naked-eye observations go back only a few thousand years at most. This means that even if Planet 9 passed close enough to Earth to leave subtle gravitational footprints in ancient sky records, we would have no way of knowing. The planet moves so slowly against the background stars that distinguishing its motion from the random positions of distant galaxies requires decades of careful comparison. The mathematics predict its position based on the orbits of other objects. But without seeing the planet directly and watching it move over years or decades, every prediction remains a best guess based on indirect evidence. 1 year, longer than all of recorded human history, the universe operates on timescales that make human civilization feel like a single breath, and somewhere in that vast, slow darkness, something is moving, patiently, silently, unhurried by anything we call time. Think about the concept of a safe distance. If you stand next to a fire, you feel the heat, you are influenced by it, you have to think about it. Walk far enough away, and the fire no longer concerns you. You cannot feel it. It cannot affect you. Distance equals freedom from influence. The object known as 2023 KQ-14 has achieved an extreme version of that freedom. Its orbit is so remote that even at its closest point to the Sun, the perihelion, it stays 6.6 billion miles away. Neptune sits about 2.8 billion miles from the Sunday. This object's closest approach is more than double that. Even when it is as close to the Sun as it ever gets, it is still flying through a zone so distant and cold that the Sun is nothing but a faint star in the sky above it. Objects like this fascinate astronomers because they should not be easily explained. Regular Kuiper Belt objects drift in and out of Neptune's gravitational influence. Neptune pushes and pulls them, sometimes flinging them into new orbits, sometimes capturing them temporarily. It is messy and dynamic. 2023 KQ-14 never gets close enough to Neptune for any of that to happen. Neptune cannot touch it. Its orbit exists entirely beyond Neptune's gravitational sphere of influence. So how did it get there? Something had to push it out to that distance in the first place. Either a close encounter with a giant planet billions of years ago flung it outward, or a massive distant object shepherded it gradually into that remote, stable zone. The stability of the orbit is the key detail. An orbit shaped by a single ancient gravitational kick tends to remain stable if nothing is nearby to keep disturbing it. The fact that 2023 KQ-14 moves in such a smooth, predictable path suggests that whatever influence originally shaped its orbit is now keeping a respectful distance. This is actually consistent with Planet 9 sitting at an enormous distance, moving on its own very slow orbit. If Planet 9 is real, and currently sitting at the far end of its elongated orbit, its gravitational influence on nearby objects would be weaker than when it is closer. The sednoid could be sitting in a relatively quiet zone while the hidden planet is at maximum distance. But here is the second thing 2023 KQ-14 tells us. Its orbital properties still broadly align with the patterns seen in other clustered distant objects. The direction of its orbit, the angle it takes, fits within the same family of orientations that motivated the Planet 9 prediction in the first place. So while its stability argues against a very close massive planet, its orientation still fits into the bigger picture of a distant massive planet exerting long-range gravitational order on the outer solar system. 2023 KQ-14 does not kill the Planet 9 theory. It reshapes it. It pushes the planet farther, the orbit wider, the search zone deeper. Every new discovery is like a clue that changes the shape of the map without erasing it. And the map, even with its constantly shifting borders, kept pointing towards something out there. Something that was still invisible, still unmeasured, and getting more mysterious with every passing year. At this point, a reasonable person listening to all of this might wonder something. We have the James Webb Space Telescope, arguably the most powerful observatory ever built by humans. We have massive ground-based telescopes in Hawaii and Chile, with mirrors the size of tennis courts. We can photograph galaxies 13 billion light-years away. We can see the first light that ever existed in the universe. So why can we not just find one planet in our own solar system? The answer is that finding Planet 9 is not a problem of power. It is a problem of precision in the face of overwhelming noise. When astronomers image distant galaxies, they know roughly where to look. They can also integrate light over long exposures, collecting photons for hours or even days, because the target is not moving relative to their field of view. The galaxy sits still against the background, and the telescope stares at it, building up enough light to see incredible detail. Planet 9 does not cooperate with this method. First, the planet is moving. Slowly, but moving. Over weeks and months, it drifts across the background stars. This means a long exposure, the kind that makes faint galaxies visible, would turn the planet into a blurry streak rather than a clear point of light. To detect a moving object, you have to take multiple shorter exposures and compare them over time, looking for something that shifts position between images. This is called a moving object search. It works well for nearby asteroids and Kuiper Belt objects, which move visibly in a single night of observation. But Planet 9 moves so slowly that detecting its motion requires comparing images taken months or years apart. And between those observations, the telescope has to be pointed at the same region of sky multiple times, which competes with all the other science programs fighting for telescope time. Second, the predicted search area is enormous. Early models suggested Planet 9 could be anywhere within a large region of sky. That zone, even after being narrowed by new discoveries like 2023 KQ-14, still covers a substantial fraction of the entire sky. Surveying all of it with enough depth to detect a planet as faint as Planet 9 would take thousands of hours of dedicated telescope time. Third, and most frustratingly, every time a new survey covers part of the search zone and finds nothing, the predicted location shifts. The absence of a detection in one area forces the models to adjust, which sometimes opens new possible hiding places in areas not yet surveyed. The planet keeps escaping the net not by moving fast, but by simply being almost everywhere we have not yet looked. The James Webb Telescope is sensitive enough to detect Planet 9's thermal signature, but pointing it at an undefined patch of sky and hoping to catch the faint infrared glow of a distant planet would require knowing where to look with much more precision than current models provide. It is less like looking for a needle in a haystack and more like knowing the needle is somewhere on a football field. At night, while 1,000 other pieces of metal are scattered across the same field, each one looking similar, the tools exist. The will exists. The planet, if real, is genuinely findable, but the precision needed to aim those tools at the right spot in the sky, that is what astronomers are still working toward. And the next generation of technology might finally be close enough to deliver it. Everything covered so far has been building a case for one answer: a single massive planet sitting in the dark, pulling on everything around it. That is the clean, dramatic explanation. One hidden world, one gravitational source. But science is not always kind enough to give us the clean answer. A group of researchers has put forward an alternative, and it is worth taking seriously. The theory starts with the Kuiper Belt, that ring of icy objects beyond Neptune. Inside the Kuiper Belt, and scattered in the space beyond it, there is a broader region called the scattered disk. This zone contains countless icy objects, many too small and faint to be individually detected. They are the debris of the early solar system, flung outward by gravitational interactions during the chaotic first billion years of the solar system's history. We have found some of these scattered disk objects, but we have only found the largest and brightest ones, the ones just big enough for our telescopes to detect. Millions of smaller objects almost certainly exist out there, too dim to see directly. Now here is the idea. What if the combined gravity of all those millions of small objects, acting together, is producing the same effect that a single large planet would produce? Individually, each icy rock in the scattered disk is tiny. Its gravitational pull is negligible, but add up millions of them, spread across a ring that encircles the outer solar system, and the total gravitational influence could be significant. A distributed source of gravity rather than a concentrated one, a ring rather than a planet. The math for this alternative model is difficult. Calculating the gravitational effect of millions of individual objects is enormously complex, requiring computational simulations that push the limits of available computing power. But some researchers have built these models and found that under certain conditions, a massive enough scattered disk can produce orbital clustering patterns similar to those observed. If this theory is correct, Planet 9 does not exist. The anomalies are real, but the cause is distributed. The solar system did not retain a hidden giant planet. Instead, it kept a vast, invisible ring of small bodies that collectively mimic one. There are challenges with this model. For the scattered disk to produce the observed effects, it would need to contain substantially more mass than current estimates suggest. The disk we observe, even extrapolating for unseen small objects, falls short of the mass needed. This does not rule the theory out, but it requires assumptions that push against what astronomers currently think they know about the outer solar system. Additionally, the scattered disk theory struggles to explain the 6-degree solar tilt with the same elegance that the Planet 9 model achieves. A ring of distributed objects does not produce the same kind of sustained gravitational torque that a single massive planet on an inclined orbit would generate. The 6-degree tilt remains much better explained by one concentrated source. But the scattered disk theory is valuable precisely because it forces the Planet 9 camp to be rigorous. It is a challenge that demands better evidence, more precise measurements, and cleaner models. Science advances fastest when competing ideas fight it out with data, and the data was about to get much stranger, because a competing theory was not just going to challenge the location of Planet 9. It was going to challenge whether Planet 9 was a planet at all. Everything discussed so far has assumed one thing. The object pulling on the outer solar system is a planet. A large, cold, icy world drifting in the dark. That is the default assumption, the one that fits neatly into existing models of how solar systems form and evolve. But a small group of physicists decided to ask a different question. What if the object is not a planet at all? In 2019, 2 researchers from Harvard published a paper that stopped a lot of people cold. They proposed that the gravitational anomalies in the outer solar system might be caused by a primordial black hole, a tiny, ancient black hole formed in the first moments after the Big Bang. captured by our solar system billions of years ago and sitting quietly in the dark ever since. Here is the part that makes this genuinely strange. This black hole would not be large. To produce the gravitational effects observed, it would only need to have the mass of roughly 5 to 10 Earths, and a black hole with that much mass would be about the size of a grapefruit. A grapefruit, sitting somewhere in the outer solar system. Black holes are not defined by their size. They are defined by their density. The mass of 10 Earths, compressed into a sphere the size of a small fruit, creates a gravitational field so intense that even light cannot escape from its surface. But from a distance, it pulls on surrounding objects exactly the way any massive object would. Its gravity at long range is indistinguishable from the gravity of a planet with the same mass. This is what makes the theory scientifically legitimate rather than wild speculation. Gravitationally speaking, a 10 Earth mass black hole and a 10 Earth mass ice giant planet would produce identical effects on the orbits of distant objects. The orbital clustering, the solar tilt, the retrograde orbiters, all of these would look exactly the same whether caused by a planet or a black hole of equal mass. The difference is that you cannot see a black hole with a regular telescope at all. A black hole emits no reflected light because it has no surface to reflect from. It emits no thermal glow the way a planet would because it has no internal structure radiating heat. A primordial black hole of this size would be completely invisible to every detection method astronomers currently use, except one. If matter drifted close enough to the black hole, it would be pulled inward and heated to extreme temperatures, briefly producing a flash of high-energy radiation. This is called accretion, but out in the cold, nearly empty outer solar system, the density of floating matter is so low that such events would be vanishingly rare and extraordinarily faint. Primordial black holes are themselves still theoretical. They were proposed as objects that could have formed in the extreme density of the early universe, fractions of a second after the Big Bang, before stars or galaxies existed. Their existence has never been directly confirmed. Some physicists believe they could make up a portion of dark matter. Others doubt they formed at all, in significant numbers, but the math allows them. And if even a small number of them exist in our galaxy, the odds of one being gravitationally captured by our solar system billions of years ago are not zero. A grapefruit-sized singularity, sitting in our cosmic backyard, completely invisible, slowly pulling the outer solar system into shape. That thought is either thrilling or deeply unsettling, depending on how you look at it. And there was one more alternative waiting, one that challenged something even more fundamental than the existence of a hidden object. Everything in astronomy runs on gravity. Every orbit calculated, every trajectory predicted, every galaxy mapped. Gravity is the foundation of it all. And the rules of gravity were written by Isaac Newton in the 17th century and refined by Albert Einstein in the 20th. Those rules have been tested millions of times and proven correct in every experiment ever designed. But there is a catch. The rules work perfectly at the scales humans can test directly. Planets, moons, spacecraft, even stars and nearby galaxies. At those scales, the math is reliable to extraordinary precision. At larger scales, things get strange. Galaxies do not behave quite the way Newton and Einstein predict. Stars at the edges of galaxies orbit far too fast for the amount of visible matter in those galaxies to explain. The standard response from mainstream science is to propose dark matter, an invisible substance that provides extra gravitational mass. Dark matter itself has never been directly detected, which is a significant problem. In the 1980s, a physicist named Mordechai Milgrom proposed a different solution. Instead of adding invisible matter to make the equations work, he suggested modifying the equations themselves. His theory, called modified Newtonian dynamics, proposes that gravity behaves differently at very low accelerations. In everyday situations, at the scales of planets and solar systems, the difference is too small to measure. But at the vast scales of galaxies, or in regions where gravitational acceleration becomes extremely weak, the modified rules produce noticeably different outcomes. Now, apply this idea to the outer solar system. In the extreme outer reaches beyond Neptune, the gravitational pull from the Sun is incredibly weak. Objects out there experience gravitational acceleration so faint it barely registers by normal standards. If modified Newtonian dynamics is correct, gravity at that scale would behave slightly differently than Newton's equations predict. Some researchers have proposed that this modified gravity, operating in the weak acceleration zone of the far outer solar system, could naturally produce the orbital clustering patterns observed among the distant icy objects. In other words, the strange alignments and grouped orbits might simply be what orbits look like when modified gravity applies, rather than evidence of a hidden planet. This theory does not require any hidden planet, no black hole, no extra mass at all, just a different set of rules for how gravity works at extreme distances. The challenge for this model is significant. Modified Newtonian dynamics struggles to fully explain the 6-degree solar tilt, the retrograde orbiters, and several other anomalies simultaneously. It handles some observations reasonably well, but requires additional assumptions to cover all of them. The Planet 9 model, by contrast, handles all of them with one unified explanation. Modified Newtonian dynamics has also faced difficulties in other contexts. Some galaxy clusters and gravitational lensing observations fit poorly with its predictions. Mainstream physics has largely stuck with dark matter as the preferred explanation for galactic scale behavior. Though the debate remains genuinely open, what modified Newtonian dynamics does, at minimum, is force humility. It is a reminder that every prediction about Planet 9 is built on gravitational equations that have never been tested at the scale of the far outer solar system. Sending a spacecraft out there is the only way to truly verify that our gravity models hold in that regime. Until then, a small but credible fraction of physicists believes the anomalies are not a mystery about a missing planet. They are a signal that physics itself is incomplete. That is a much bigger problem, and it is one nobody has solved yet. The Kuiper Belt stretches from just beyond Neptune, at roughly 2.8 billion miles from the Sun, out to about 50 astronomical units, which works out to approximately 4.6 billion miles. It contains hundreds of thousands of icy objects, ranging from small chunks of rock and ice to dwarf planets like Pluto and Eris. For a long time, astronomers thought the Kuiper Belt was a relatively straightforward leftover, the debris of planetary formation that never got incorporated into a major planet, frozen and preserved at the edge of the solar system like a cosmic junkyard. Then they started looking more closely at its structure. The Kuiper Belt has a hard edge. At roughly 50 astronomical units, the density of objects drops sharply. Beyond that point, the belt thins out dramatically. This is strange, because standard formation models predict the belt should extend much farther outward with a gradual taper rather than a sudden cutoff. Something carved that edge. Astronomers also noticed that the Kuiper Belt is divided into different populations. Objects in the inner regions follow relatively circular orbits and appear to have been there since the early solar system. Objects in the outer regions have more scattered, elongated orbits, as though they were disturbed and flung around by some gravitational interaction at some point in the past. And then there is a gap, a zone inside the Kuiper Belt, where objects are conspicuously sparse, an absence where there should be more debris. Planet 9 offers an explanation for all of this. If it spent time in the inner solar system long ago, the leading model for how Planet 9 ended up in the far outer solar system involves it forming much closer to the Sun, among the other gas giants, and then being gravitationally kicked outward by a close encounter with Jupiter or Saturn early in the solar system's history. This kind of ejection event would have sent the young planet on a long, looping orbit that initially brought it back close to the inner solar system repeatedly before its orbit stabilized farther out. During those early close passes, before its orbit settled into the deep outer region, Planet 9 would have swept through the Kuiper Belt repeatedly. Each pass would have scattered objects, cleared gaps, and carved structure into the belt. The hard outer edge could be the result of Planet 9 sweeping through and throwing anything beyond it into unstable orbits. The population divisions could be the scars of those ancient passes. This reshaping would have happened billions of years ago, during the chaotic early period of the solar system. By the time humanity evolved and looked up at the sky, all that remained were the structural scars in the Kuiper Belt, the fingerprints of a rogue giant that had long since retreated into the dark. The Kuiper Belt, in this picture, is not just a junkyard, it is a crime scene, and the evidence written into its gaps and edges tells a story of something powerful that passed through and left permanent marks. What it did to the Kuiper Belt was dramatic, but what it may have done to individual worlds drifting through the outer solar system was even more direct. Gravity is patient. It does not rush. It does not announce itself. It simply pulls, constantly and silently, and over time that pull can accomplish extraordinary things. Dwarf planets exist in surprising numbers in the outer solar system. Pluto, Eris, Makemake, Haumea, and dozens of other confirmed or suspected dwarf planets drift through the Kuiper Belt and beyond. Many of these worlds have moons. Pluto has 5, Haumea has 2. Eris has 1 known companion. These moons are loosely bound to their parent worlds. The gravitational connection between a dwarf planet and its moon is much weaker than the connection between Earth and our moon, because the dwarf planets are far smaller and less massive. Their gravitational grip on their companions, while real, is relatively gentle. Now imagine one of these dwarf planet systems drifting into the gravitational neighborhood of something 10 times heavier than Earth. Planet 9's gravity does not shut off at a clean boundary. It extends outward in every direction, weakening with distance but never truly stopping. A dwarf planet passing within a certain range of Planet 9 would feel that tug, so would its moon. The dwarf planet itself is more massive and would hold onto its orbit better, but the moon, being lighter and orbiting at a distance from the dwarf planet, would be more susceptible to being pulled away. If the geometry were right, with the moon on the side of the dwarf planet facing Planet 9 during a close enough pass, the gravitational difference between the pull on the moon and the pull on the dwarf planet could be enough to strip the moon free. This is called tidal stripping. It happens with galaxies, where larger galaxies pull stars away from smaller ones during close passes. It happens with star clusters, which gradually lose their outer stars to the gravitational field of the galaxy over billions of years. The same physics applies at smaller scales. In the outer solar system, where dwarf planets orbit slowly and passes between objects occur over millions of years, tidal stripping by a massive hidden planet would be a slow and gradual process. Over the age of the solar system, Planet 9 could have stripped moons from multiple passing dwarf planets, those moons then either being captured into orbit around Planet 9 itself or flung into new, irregular orbits in the outer solar system. Some astronomers have pointed to the collection of irregular, distant moons orbiting the known giant planets as partial evidence of this kind of capture process. Objects on strange orbits that do not match the pattern of natural moon formation might be captured bodies that were destabilized by gravitational encounters in the past. Planet 9, if real, would be the most powerful gravitational presence in the outer solar system by far. Anything passing within a few billion miles of it over billions of years would have had its orbit reshaped at minimum, and its moons stripped away at worst. The outer solar system is not the quiet, frozen museum it appears to be from a distance. It is a place where slow gravitational violence has been playing out for billions of years, and the architect of much of that violence might be sitting in total darkness right now, pulling on everything nearby, completely unknown to us. But unknown does not mean unfindable, and the next decade may change everything. Close your eyes for a moment and imagine you are standing on the surface of Planet 9, except you cannot stand. There is no surface. Planet 9 is an ice giant, which means its outer layers are deep, crushing gas. You are floating instead, suspended somewhere in the upper atmosphere, high enough that the pressure has not yet become lethal. The first thing you notice is the darkness. It is not the darkness of a moonless night on Earth. There is no scattered glow from a city somewhere, no faint light bouncing off clouds. The darkness here is absolute, a deep, total blackness in every direction except one. In one direction, there is a bright point of light. That is the Sunday. From this distance, it looks exactly like a star, brighter than any other star in the sky, but unmistakably a point, not a disk. No warmth reaching your face. No light illuminating the ground below. Just a single white-blue pinpoint blazing against a sky full of other stars. You look at the stars and realize something unsettling. They are beautiful, more of them than you could ever count on Earth, because there is no atmosphere to scatter their light and no star bright enough to drown out the fainter ones. The Milky Way stretches across the sky in brilliant detail, a river of light so dense it almost looks solid, but it is cold, colder than anything on Earth, colder than the coldest place on the Antarctic plateau in the dead of winter. The temperature here hovers near negative 455 degrees Fahrenheit, just a few degrees above absolute zero, the coldest temperature the universe allows. Your breath would freeze before it left your mouth. Any water you carried would turn to rock-hard ice in an instant. The methane and nitrogen drifting through the atmosphere around you are not gases here. They are ice crystals, suspended in slow currents, glittering faintly when they catch the distant starlight. The wind would be powerful despite the cold. Internal heat from the planet's core drives enormous atmospheric currents, rivers of churning gas, hundreds of miles wide, moving at speeds that would dwarf any storm on Earth. But because there is no sunlight, these storms are invisible. Dark winds in a dark sky. Above you, faintly, you might be able to see the distant band of the Milky Way, shifting slightly as the planet turns. And if you watched patiently over years of observation, you might just barely notice the bright star of the sun moving against the background of other stars, very slowly, almost imperceptibly. One full circle would take between 10,000 and 20,000 years. That is the tempo of this place. That is the scale of time Planet 9 operates on. Everything here is vast, cold, patient, and dark. From Earth, it is invisible. From here, Earth would not be visible either. Our home planet, viewed from Planet 9, would be an invisible speck lost in the glare of the Sunday. Two worlds. The same solar system, completely unaware of each other. Until now, imagine taking a photograph of a crowded stadium from across a field. Thousands of faces are visible. Now imagine you are trying to identify one specific person who is walking slowly through the crowd, but you can only tell them apart from the other people by watching for movement over the course of several hours. That is roughly the challenge of confirming Planet 9 from a single observation. When a telescope spots a faint point of light in the outer solar system search area, that point of light could be many things. It could be a distant galaxy, billions of light years away, appearing as a faint smudge. It could be a known asteroid or Kuiper Belt object, not yet in the catalogue. It could be an artifact in the detector itself, a smear of noise that happens to look like a real object. Or it could be Planet 9. The way astronomers separate solar system objects from background sources is through parallax and proper motion. A solar system object, even one moving slowly, is physically nearby. As Earth moves in its own orbit around the Sun, nearby objects appear to shift position against the distant background stars. This shift is called parallax. Background galaxies, being billions of light years away, show no measurable parallax at all. Additionally, solar system objects genuinely move. Over weeks and months, they drift against the background stars at a rate that reflects their actual orbital speed. A distant galaxy does not move relative to the background because it is part of the background. By taking two images of the same patch of sky, separated by weeks or months, and comparing them carefully, astronomers look for any point of light that has changed position. Anything that moves is a solar system object. Anything that stays fixed is a background source. For Planet 9, the movement would be extremely slow, slow enough that you might need months between images to see a clear shift. This is why the search cannot be done in a single night. The planet would not move enough in one observing session to stand out clearly from the noise of background objects. And the search area is enormous, covering the entire predicted zone with repeated observations, separated by enough time to detect the slow motion of a distant planet, requires years of systematic sky surveys, thousands of hours of telescope time, massive storage, and computational systems to compare the images automatically and flag candidates. Teams around the world have been running exactly this kind of survey. The Outer Solar System Origins Survey, the Dark Energy Survey, Pan-STARRS, and others have each covered portions of the predicted search zone. Each survey has found new Kuiper Belt objects, new distant bodies, new pieces of evidence, but none has found Planet 9 itself. The absence of a detection in a given region of sky is useful. It rules out that zone, shrinks the possible hiding areas, and tightens the models. Every blank patch of sky surveyed makes the eventual discovery more likely by eliminating possibilities. Astronomers are methodically shrinking the haystack. The needle is still in there, and a new instrument being built right now may finally be sensitive enough to find it in a single sweep. The search is not stalling, it is accelerating, and the next chapter of this story has not been written yet. In the mountains of Chile, at an elevation of roughly 8,800 feet, construction has been completed on one of the most ambitious telescopes ever built. It is called the Vera C. Rubin Observatory, named after the astronomer who discovered the first convincing evidence for dark matter in galaxies, and it may be the instrument that ends the Planet 9 debate once and for all. The Rubin Observatory is designed for something specific. It is not meant to stare at one object for hundreds of hours the way the James Webb Space Telescope does. Instead, it is built to survey. Every few nights, the Rubin telescope will photograph the entire visible sky, every patch, every corner, every faint smudge in the darkness. Its camera is the largest digital camera ever built for astronomy, with a resolution so high that a single image would fill thousands of standard computer screens. Its mirror collects light efficiently enough to detect objects roughly 100 times fainter than anything visible to the naked eye under perfect conditions. And it does this repeatedly. The same patches of sky, photographed again and again over a 10-year survey called the Legacy Survey of Space and Time. Every image from every visit to each patch of sky gets compared automatically by software that flags anything that has moved. This is exactly what the Planet 9 search needs: wide coverage, repeated observations, automated motion detection, deep sensitivity to faint, cold, slowly moving objects. Estimates from the astronomical community suggest that if Planet 9 exists anywhere within its predicted orbital range, and is not currently hiding directly behind the Milky Way's densest star fields, the Rubin Observatory survey should find it within its 10-year run. Some optimistic estimates say a detection could come within the first 2 to 3 years, assuming the planet falls in a region with relatively clean background. The survey officially began its full science operations in 2025. That means the countdown is already running. If Planet 9 is found, the discovery will reshape our understanding of solar system formation. It will confirm that our solar system has a structure more complex than any textbook currently describes. It will give planetary scientists a nearby ice giant to study up close, in relative terms, in ways currently impossible for Uranus and Neptune. If it is not found, that is equally significant. An exhaustive survey of the predicted zone returning nothing would force a fundamental reconsideration of all the models. It would push the scattered disk theory or the modified gravity explanation back to the center of the debate. It would mean the orbital anomalies are caused by something other than a planet, and the search for that something would begin in earnest. Either way, the Rubin Observatory is going to answer the question. The era of uncertainty is approaching its end, but even as astronomers prepare for that answer, a deeper question was growing louder. If Planet 9 exists, where did it come from? And what did it do to the early solar system on its way out? Right now, Every textbook on planetary science describes our solar system as following a clean pattern: rocky planets close to the Sunday gas giants farther out, an icy belt of debris beyond that. 8 planets, neatly organized, the product of a well-understood process that began 4.5 billion years ago. Finding Planet 9 would erase that picture. The current model of solar system formation, called the NICE model, describes how the giant planets formed and then migrated to their current positions through gravitational interactions with each other and with the debris disk surrounding. The young Sunday Jupiter moved inward and then outward. Saturn, Uranus, and Neptune shifted and jostled. The whole system rearranged itself over hundreds of millions of years before settling into the configuration we observe today. Planet 9 does not fit cleanly into this picture. If it is real, it is a full-sized ice giant that the model did not predict and does not currently accommodate. It means the early solar system had 5 major giant planets, not 4. One of them was flung outward by gravitational interactions to an orbit so enormous that it barely feels like part of the same solar system anymore. That is a significant revision. The NICE model would need to be expanded or replaced. New simulations would have to account for a 5th giant and the cascade of gravitational effects it would have caused during the early chaotic period. The structure of the Kuiper Belt, the late heavy bombardment that scarred the inner planets billions of years ago, the distribution of comets, all of these would need to be reanalyzed with a 5th giant in the picture, but the implications extend beyond our own solar system. When astronomers study planets around other stars, they regularly find something our solar system seems to lack: super-Earths. Planets with masses somewhere between Earth and Neptune, sitting in all kinds of orbital positions, are the most common type of planet found around other stars. Yet our solar system has no super-Earths. Nothing in that mass range between Earth and Neptune at any distance, except, potentially, Planet 9. If Planet 9 is real, it might represent our solar system's super-Earth, the planet that should be filling a gap in our planetary lineup, but one that was kicked to the outermost edge of the system billions of years ago. Finding it would explain why our solar system looks unusually sparse compared to others. We did not fail to form a super-Earth. We formed one and then lost it to the outer darkness. This changes how astronomers think about solar system architecture everywhere. It suggests that planets being scattered to extreme outer orbits might be more common than previously thought. Other solar systems might have their own hidden giants, sitting in orbital regions too faint and distant for current technology to detect. Planet 9, in other words, would not just be a discovery about our solar system, it would be a discovery about planets in general. The full weight of what that means has not yet been absorbed. About 4 billion years ago, the inner solar system went through a period of extraordinary violence. Scientists call it the Late Heavy Bombardment. The Moon, Mars, and Mercury all show the scars of this period in the form of massive impact craters, some of them hundreds of miles across, that formed during a relatively short window of time. Something triggered this bombardment. Something disturbed the orbits of vast numbers of asteroids and comets, sending them crashing inward toward the rocky planets at a rate far higher than the background level of random impact. The leading explanation, based on the NICE model, is that the giant planets shifted their orbits during this period, crossing gravitational resonances that destabilized the asteroid belt and the Kuiper Belt simultaneously. Jupiter, moving slightly outward, or Saturn migrating inward, could have sent cascades of debris flying toward Earth, the Moon, and Mars. If Planet 9 was part of the early solar system and was then flung outward during this same period, its departure could have been one of the triggers for the bombardment. Think about what happens when you pull a marble out of a bag full of marbles quickly. The other marbles shift. Some fall out. Some roll into each other. A large planet being gravitationally ejected from the inner giant planet region would not leave quietly. Its departure would send gravitational ripples through the system, pushing other objects into new orbits, potentially destabilizing large populations of asteroids and sending them on paths toward the rocky inner planets. Earth was young when this happened. The crust was still cooling. The oceans were barely formed. The impacts during the late heavy bombardment were powerful enough to vaporize large amounts of seawater and melt surface rock. Some researchers believe this period delayed the emergence of life on Earth by hundreds of millions of years. If Planet Nine's departure contributed to that bombardment, then the most violent chapter in Earth's early history has a connection to a world still sitting in the outer solar system today. The ghost planet and the scarred moon would be linked across 4 billion years of history. There is also a more immediate implication. If Planet 9 is still slowly circling on its enormous orbit, its gravitational influence on the Oort cloud and the scattered disk has not stopped. It is still, right now, nudging long-period comets into new paths. Some of those comets end up on trajectories that bring them through the inner solar system. The history of giant comet impacts on Earth is not disconnected from Planet 9. If this planet is real, it is an active participant in the ongoing dynamics of comet delivery to the inner solar system. An unseen hand, still at work. That is not a comfortable thought, but it is a scientifically honest one. When the Kepler Space Telescope began cataloguing planets around other stars in 2009, it found something surprising. The most common type of planet in the galaxy is one that does not exist in our solar system: super-Earths. Planets with masses between 1 and 10 times that of Earth, sitting in close to medium orbits around their stars. They show up around roughly half of all Sun-like stars surveyed. They are not a rare exception. They are the default. Our solar system has 4 rocky planets, all of them less massive than 2 times Earth. Then a huge gap. Then 4 giant planets starting with Jupiter. Nothing in between. No super-Earth at any distance from the Sunday. The gap in our planetary lineup is conspicuous by galactic standards. Astronomers have proposed several explanations. One popular idea, called the Grand Tack model, suggests Jupiter formed farther out and then migrated inward toward the Sun before reversing course. During that inward migration, Jupiter would have swept through the zone where super-Earths typically form, scattering the raw material of planet formation and preventing any super-Earth from assembling. This model has merit, and it explains several features of the inner solar system, but it is not the only option. Planet 9 offers a different answer. What if our solar system did form a super-Earth, but it was ejected before we could document it? A planet forming in the zone between the inner rocky planets and Jupiter, in the mass range of 5 to 10 Earths, could have been caught in a gravitational battle between Jupiter and Saturn during the chaotic early period of the solar system. The tug-of-war between those 2 massive worlds could have sent our nascent super-Earth flying outward, first to a close outer orbit, then gradually drifting to the enormous distance it occupies today. In this story, our solar system is not unusual for failing to produce a super-Earth. It produced one and then lost it. The super-Earth is still there, just unimaginably far away and invisible. This reframing has a powerful effect on how we think about Earth and life. If Jupiter had not ejected this planet, or if the ejection had happened differently, the super-Earth might have settled into an orbit in the habitable zone, closer to the Sun, where liquid water could exist on its surface. Earth, in that scenario, might not have formed at all, or might have been pushed into a different orbit by the gravitational presence of the super-Earth. The fact that Earth exists, sits in the habitable zone, and supports life might depend on Planet 9 having been thrown out of the inner solar system at exactly the right time and in exactly the right direction. Our existence may be tied to an invisible planet most people have never heard of. That thought deserves a moment of quiet. Science is not a vote. Popularity does not determine truth. And a significant number of respected astronomers have looked at the same data that inspired the Planet 9 hypothesis and reached a completely different conclusion. Their argument centers on a concept called observational bias. Here is how it works. Astronomers do not observe the sky randomly and evenly. Telescopes are pointed at specific regions for specific reasons. Survey programs have scheduling constraints. Certain parts of the sky are easier to observe from certain locations. Certain brightness thresholds affect what objects get included in a catalogue. The distant objects used to build the case for Planet 9 were not discovered through a perfectly uniform sky survey. They were found in patches, during observations motivated by other science goals, with equipment that had specific sensitivity limits. The original sample of 6 clustered objects was small and came from surveys that were not designed to avoid bias. In 2019, a team of researchers published a study directly addressing this issue. They took the orbital data for the distant objects and applied a statistical correction for observational bias. After accounting for the fact that certain orbital orientations are simply more likely to be discovered given where and how telescopes actually look, they found that the apparent clustering largely disappeared. In other words, the 6 objects pointing in the same direction might not be genuinely pointing in the same direction. They might just be the ones astronomers happened to find, because those orbital orientations were more visible from where the surveys were conducted. If this analysis is correct, there is no anomaly to explain. The outer solar system is behaving exactly as expected. The apparent clustering is an artifact of incomplete surveying, not a signal from a hidden planet. The Planet 9 camp pushed back. Batygin and Brown argued that even with bias corrections applied, a statistically significant clustering remained. The debate over exactly how to apply the bias corrections and how large the residual signal is after correction is genuinely unresolved. Different teams using different methods get different answers. More objects need to be discovered. A larger sample, found through unbiased wide sky surveys, would either strengthen or dissolve the clustering signal. The Vera Rubin Observatory's survey, covering the whole sky systematically, was designed partly to address this exact problem. Its results will be authoritative precisely because they will not suffer from the selection effects that plague earlier targeted surveys. The anti-Planet 9 scientists are not fringe voices. They are rigorous researchers following the data. Their critique is scientifically legitimate, and the possibility that the whole mystery is a statistical illusion is very much alive. Science lives in that tension, competing explanations, each with honest intellectual backing. The answer is in the data, and the data is still being collected. Humans are pattern-finding machines. We cannot help it. It is built into us so deeply that we see faces in clouds, hear words in random static, and find meaning in coincidences. This drive to find patterns is one of our greatest cognitive tools. It is also one of our greatest cognitive traps. In science, the version of this trap is called confirmation bias. Once a compelling hypothesis exists, there is a natural human tendency to see confirming evidence more clearly than disconfirming evidence. Objects that fit the prediction feel important. Objects that do not fit get categorized as outliers and moved aside. The Planet 9 hypothesis is a rich environment for this kind of bias. When Batygin and Brown published their 2016 paper, it was a genuinely exciting moment for planetary science. The idea of a hidden 9th planet captured public attention instantly. Follow-up surveys, motivated by the prediction, went looking in the predicted region of sky. New, distant objects discovered in or near the predicted orbital zone received significant attention. Objects discovered elsewhere in the outer solar system, with orbits that did not fit the clustering pattern, received less attention. This is not a criticism of any individual scientist's integrity. It is a description of how human attention and scientific resources naturally flow. A compelling hypothesis acts like a magnet, drawing observations, funding, telescope time, and intellectual energy toward the predicted region. The problem is that a hypothesis tested primarily by data collected in the region it predicts will always appear more supported than it might actually be. You look where you expect to find something, and you find things consistent with the expectation. That does not prove the expectation is correct. It proves you looked in the right direction, which you already knew because the hypothesis told you where to look. True confirmation requires finding evidence in places and ways the hypothesis did not predict. It requires the failed searches to be as thoroughly documented and analyzed as the successful ones. It requires a systematic, unbiased survey of the full sky, not just the predicted zone. This is why the Vera Rubin survey matters so much. It covers the whole sky, including regions where Planet 9 should not be. If the clustering pattern is real and not a product of biased sampling, a complete sky survey should still show it. The clustered objects should still outnumber the randomly oriented ones, even when the data collection is perfectly even. If the clustering disappears or weakens significantly when measured against a complete, unbiased dataset, the scientific community will have to accept that the pattern was partly or entirely a product of how humans searched rather than what the solar system actually contains. This does not mean the search was wasted. Every new distant object discovered, biased or not, adds to our understanding of the outer solar system, but the Planet 9 hypothesis itself would need serious revision. Science is uncomfortable with uncertainty, but the most honest answer available right now is that the jury is still genuinely out. The data that will settle it is being collected as you listen to this. Every night, the Rubin telescope opens its eye. The answer gets a little closer. Of all the challenges in the Planet 9 search, the black hole scenario presents the most extreme version of the detection problem. A planet, however dark and cold, still has a surface. It still reflects some light. It still radiates internal heat. These are faint signals, but they are real signals that telescopes can theoretically detect. A primordial black hole has none of that. It has no surface to reflect light from. It produces no thermal glow. From a gravitational standpoint, it is indistinguishable from a planet of the same mass. From an observational standpoint, it is the darkest possible object in the universe. So how would you find it? The most promising method involves watching for what happens when things fall into the black hole. Even in the cold, empty outer solar system, small quantities of dust, gas, and occasionally small rocky objects drift through space. If a primordial black hole exists out there, it would occasionally capture some of this material. As the material spirals inward toward the black hole's event horizon, it gets compressed and heated to extreme temperatures, briefly emitting a burst of radiation before crossing the point of no return. This process, called accretion, produces high-energy radiation, including X-rays and gamma rays. In the dense environment near a black hole in a galaxy center, accretion produces spectacular luminosity that can be seen across billions of light years. In the near vacuum of the outer solar system, the same process would be almost imperceptibly faint. The rate of material falling into such a small black hole in such an empty region of space would be tiny. But tiny is not zero. Some researchers have proposed that with sensitive enough detectors, the occasional flash of high-energy radiation from outer solar system accretion events might be detectable. Another method involves something called the Hawking radiation prediction. Theoretical physicist Stephen Hawking proposed that black holes slowly lose mass by emitting a faint radiation due to quantum effects at the event horizon. For a black hole the size of a grapefruit with the mass of several Earths, this radiation would be extraordinarily faint, almost certainly undetectable with any current instrument. A third approach uses lensing. When a massive object passes between Earth and a background star, the object's gravity bends the starlight and produces a brief brightening of the star. This is called gravitational microlensing. A primordial black hole moving slowly through the outer solar system would produce microlensing events as it slowly drifts in front of background stars. These events would be rare, faint, and brief. But surveys designed to detect microlensing, including some already operational, would theoretically pick them up. If a microlensing event were detected in the predicted region of sky and no visible object were found at the lensing location, a primordial black hole would become a serious candidate. Finding nothing with optical telescopes would not be a dead end. It would be a clue pointing towards something stranger than a planet. Planet 9's orbit is not circular. Like the orbits of the distant icy objects it influences, Planet 9 itself travels on a highly stretched, elongated path. At one end of that path, its nearest point to the Sun, it may come within roughly 200 astronomical units of the Sunday. At the far end, it retreats to perhaps over 1,000 astronomical units away. 200 astronomical units works out to roughly 18.5 billion miles. That is still vastly farther from Earth than any known planet. Earth sits about 100 million miles from the Sun, which puts Planet 9 at the near end of its orbit, about 185 times farther away from the Sun than Earth is. At that distance, Planet 9's direct gravitational pull on Earth would be negligible. The Sun's gravity holds Earth in its orbit with vastly more force than any object at that distance could exert. Earth is not going to drift toward Planet 9. That is not the concern. The concern is indirect influence, played out over millions of years. Planet 9's gravity continuously nudges the orbits of objects in the outer solar system. The Oort cloud, a vast spherical shell of icy bodies surrounding the entire solar system at distances of thousands of astronomical units, is susceptible to gravitational disturbances. When something tugs on Oort cloud objects, it can send them falling inward on extremely long, looping paths through the solar system. Long-period comets, the kind that take thousands or tens of thousands of years to complete one orbit, come from the Oort cloud. They fall inward, sweep past the inner planets, sometimes spectacularly close to Earth, and then swing back out into the dark. Planet 9, if real, has been influencing Oort cloud dynamics for billions of years. Some fraction of the long-period comets that have passed near Earth throughout its history arrived on those paths, at least partly because of Planet 9's long-range gravitational disturbances. This is an ongoing process. Planet 9 is likely nudging new Oort cloud objects onto inward trajectories right now, on timescales that will play out over millions of years before those comets ever reach the inner solar system. The direct risk to Earth from this process is not zero, but it is also not something that changes meaningfully on human timescales. The occasional large comet impact is a feature of Earth's geological history, not a recent development. If Planet 9 is real and has been operating this way for billions of years, it has already been a background factor in every major impact event in Earth's history. Understanding it does not make the Earth less safe, but it does reframe how we think about the long-term stability of our cosmic neighborhood. The solar system is not a static clock ticking quietly. It is a dynamic system, still being shaped by forces that act over timescales we can barely imagine. Planet 9, if real, is one of those forces, and it has been operating in silence, just outside the reach of human awareness, for as long as Earth has existed. The Oort cloud is the outermost region of our solar system. It is not a ring or a belt like the Kuiper belt. It is a vast spherical shell of icy objects completely surrounding the solar system in every direction. It starts at roughly 2,000 astronomical units from the Sun and extends outward to nearly 100,000 astronomical units, which puts its outer edge about 1.5 light years away. 1.5 light years. That is almost close enough to another star. The Oort cloud marks the point where the Sun's gravitational grip gives way to the gravitational tugs of neighboring stars. This makes the Oort cloud uniquely vulnerable to outside disturbances. Passing stars, molecular clouds, and even the overall gravitational field of the Milky Way can reach into the outer Oort cloud and nudge objects there onto new paths. Some of those nudged objects fall inward, becoming the long-period comets that occasionally sweep through the inner solar system on orbits, taking thousands of years. Planet 9 would add another disturbing influence, one much closer to home, a planet sitting deep inside the solar system, but still at extreme distances from the Sun, would have a sustained, long-term gravitational reach into the inner Oort cloud, the closer portion of the shell starting at a few thousand astronomical units. As Planet 9 traces its enormous oval orbit, it would periodically swing closer to different portions of this inner Oort cloud, tugging objects in those regions. Over millions of years, repeated passes by Planet 9 would gradually destabilize certain families of Oort cloud objects. Some would be pushed into tighter orbits that bring them closer to the Sunday, Others might be flung outward past the cloud entirely and lost to the interstellar void. The ones pushed inward become comets. Long-period comets arriving in the inner solar system from the Oort cloud do not come from random directions. Studies of their orbital origins show they tend to cluster into certain regions of the sky, suggesting that the disturbing forces that launched them are not uniformly distributed. Some researchers have proposed that these cluster patterns could be used to reverse engineer the position and orbital properties of Planet 9. It is another piece of indirect evidence, a gravitational whisper from the outer darkness, and it means that the icy visitors that occasionally blaze across Earth's sky, lighting up for weeks as they heat up near the sun before retreating into the dark, are not random. Some of them were set on their path by the quiet influence of an unseen world on the far edge of our solar system, millions of years before they were visible to any human eye. Comets have been arriving from that direction for billions of years. We just never knew what was sending them. That changes how this story ends, because the last chapter is not really an ending at all. Everything covered in this story leads to one moment, a moment that is coming within the next decade, possibly within the next few years. The Vera Rubin Observatory is imaging the sky right now. Every few nights, its enormous camera captures a new mosaic of the southern sky, building a database of every point of light visible from its mountaintop in Chile. Each image gets compared to the last. Every moving object gets flagged. The system processes more data in a single night than most previous sky surveys produced in a year. If Planet 9 is sitting in the southern sky, within the region already covered by the survey, Rubin will detect it. The question is when, not if, assuming the planet is there. The northern sky presents a more complex challenge. The Rubin Observatory cannot observe far into the northern hemisphere from its location in Chile. The regions of sky above the celestial equator require northern hemisphere telescopes. Several are being brought to bear, including upgraded survey instruments in Hawaii. The predicted search zone has two lobes, one accessible from the south and one from the north, and both need to be covered systematically. Meanwhile, the James Webb Space Telescope remains a powerful backup detection method. If a candidate position is identified through any means, pointing Webb at that location would confirm or rule out a thermal infrared source quickly. Webb's sensitivity at the relevant wavelengths is extraordinary. A Planet 9-sized object within the predicted distance range would be detectable in a reasonable observing window. If Planet 9 is found, the announcement will be one of the largest in the history of astronomy, a ninth planet, a super-Earth in our own solar system, a world that has been sitting there since the formation of the solar system, invisible and unknown, until a generation of astronomers built the tools precise enough to find it. The discovery would trigger immediate follow-up campaigns across every observatory on Earth and in space. The entire outer solar system science community would reorganize around this new anchor point. If Planet 9 is definitively not found after the full Rubin survey is complete, that result will be equally historic. It will mean the orbital anomalies that inspired the hypothesis are caused by something other than a hidden planet. The scattered disk theory, the modified gravity explanation, or some entirely new model will need to step forward and account for the evidence. The non-detection will force a scientific reckoning. Either answer is extraordinary. A discovery would mean the solar system is more complex, more populated, and more strange than we thought. A non-detection would mean the laws of physics at the edges of our solar system are not quite what we thought. Both outcomes reshape something fundamental. The signals are real, the anomalies are real. Something in the outer solar system is either a hidden world or a gap in our understanding of reality itself. The telescopes are open, the data is flowing, the answer is almost within reach.